Message 10981, January 27, 95, 1817. From Norman Wooten. To David Wyland. Subject: MRA testing. David, you were correct to assume that we had thought out the testing procedure, and yes, to answer your question, we knew exactly what the outcome of the test would be by adding a lump resistance to the circuit. It kills the over-unity effect dead as hell. All three of the testing parties were told that this would happen. Now if you would please go back to the starting point and read the whole thing over, then you will not come back and suggest placing a lump resistance value anywhere in the input circuit to derive a current value. It just cannot be done this way, for it completely alters the MRA into, as Hal stated, an ordinary series resonant transformer circuit. Put you thinking cap on, for there has to be a method of determining input current and not close the P channel. What would you say if I told you that Joel and I fine-tuned a MRA last night and had the voltage and current waveforms exactly 180 degrees out of phase at the input of the MRA? See, there is something real peculiar here, for between the piezo and the coil the phase angle was 90 degrees. Comments. Norm. Message 10994, January 28, 95, 1:15. From David Wyland. To Norman Wooten. Subject: MRA testing. I hear you about the lump resistance. However, some resistance insertion must be possible, at least of the order of the DC resistance of the wires, perhaps 0.01 ohms. This can be estimated by wire tables for 20-gauge wire. With a very small resistance plus an amplifier, you should still be able to get a current waveform reading. Having the voltage and current 180 out seems strange. Could be, but I would check by substituting a DC resistance for the MRA to check polarity to be sure. Strange things happen to phase with high-Q resonance circuits near resonance. Note, the MRA circuit must have some effective resistance in it. Real amplifiers have some DC output resistance, closed loop or no. It sounds like the trick is to measure the current without disturbing the circuit. You can still try the current probe too. The ultimate test will be to measure the DC current into an efficient, low-power drive amplifier. If the current to the amplifier drops, and don't forget to decouple it with a cap to make sure the current you are measuring is DC, you move into the good region, then you are in good shape. The amplifier current method is the ultimate method. The DC output current must be enough to drive the amplifier with some left over for the system to be over unity as a whole. Say again what drive voltage, peak to peak, you are using? Good luck. Dave Wyland. Message 11037, January 30, 9500, 55. From Joel McLean. To David Wyland. Subject: black box test. Hi David. The MRA starts out below unity, and builds up steam over an hour. It takes time for the harmonics to reach their peak. You can watch it happen at increments. The secondary side of the input amp XFMR belongs to the MRA, so if you need to add resistance, add it to the primary side. When you add it to the secondary side, you modify the device under test. Look at it this way: if your car starts rolling down a hill, you can stop it with very little resistance at first. You can also stop the MRA with very little resistance at first. That's how transistor circuits are designed, so that resonances won't build up and croak them. Add a small resistance to stop them when they are still small, so they can't grow. You don't have to be in the circuit to measure the power to it. If you want to black box the MRA, don't put anything extra in the box, put it outside, ahead, of the box. Look at what is going on in your amplifier: transistors forced near cutoff, AC line current dropping below standby. Then look at the nice robust DC power off your bridge. Then go ahead and build the circuit to make it power itself. Joel. Evaluation of Magnetic Resonance Amplifier, MRA. Institute for Advanced Studies / Earth Tech International, Incorporated. 4030 Breaker Lane, Austin, Texas 78759-512, 346, 3848. H. E. Puthoff and Scott Little. January 20, 1995. Abstract tilde. An MRA device provided by Joel McLean and Norman Wooten was tested for power efficiency. The MRA is essentially a power converter, driven by an audio frequency AC voltage and producing a DC output. Our tests included meter measurements, made in the manner employed by McLean and Wooten, and digital oscilloscope measurements, which provided high-resolution recording of input voltage and current traces. Our meter measurements duplicated the results reported by McLean and Wooten, which would appear to indicate over unity, 100% efficiency, performance at certain frequencies, but only because the reactive behavior of the system is not properly taken into account by this measurement procedure. The digital oscilloscope measurements, which correctly account for the effects of circuit reactance, yielded a nearly constant 50% efficiency at all frequencies. Introduction. The MRA device we tested consisted of a piezoelectric transducer connected in series with the primary of a specially constructed, hand-wound transformer. The transformer has a ferrite core and the secondary is connected to a full-wave bridge whose output is connected to a load. McLean and Wooten computed AC input power by determining an equivalent resistance R of the MRA, and then substituting that value R, and the closed-circuit MRA input voltage V, into V2/R to calculate an input power. They determined this equivalent resistance by substituting a decade resistance box in place of the MRA to find the resistance that would yield the same connected circuit driving voltage. Such a procedure is appropriate for purely resistive loads. In their most recent tests, McLean and Wooten used a small DC motor as a load for the MRA. We used the motor initially to confirm proper operation of our MRA test bed, but replaced it with a 130 ohm resistor to eliminate commutation noise for the tests described below. We also attached a 30,000 microfarad filter capacitor across the load resistor to smooth out the DC to ensure accurate measurement with common digital meters. We used two Micronta 22, 185A meters, one in series with the load to measure current, and one connected across the load and the other meter to measure total voltage delivered to the load and current meter. Total output power is the product of these two quantities. To generate the 34 kHz signal needed to drive the MRA, we used a Tech FG504 signal generator amplified with a Pioneer H100, a modern solid-state 160-watt audio power amplifier without output transformers. To duplicate the performance of McLean and Wooten's Radio Shack MPA, 45, 35-watt amplifier, we had to add series L, 34 microhenries, and R, 11.68 ohms, to our amplifier. Without the series R, we only observed a 0.10 volt droop when driving the MRA at resonance. McLean and Wooten's amplifier exhibited a 1.58 volt droop under this loading. Without the series L, the anomalous effects were still present but substantially lower in magnitude than those observed by McLean and Wooten. With our amplifier thus modified by the addition of these elements, we have duplicated the McLean-Wooten driver amplifier setup precisely. We used a Lecroy scope station 140 100 MHz digital oscilloscope with simultaneous sampling on two channels to measure MRA input voltage and current. Current was sensed as the voltage drop across the 11.68 ohm resistor placed in series with the amplifier output. This resistor was made by placing two 22 ohm, 2-watt carbon comp resistors in parallel to provide the desired resistance with a minimal inductance. Procedure. We conducted a series of measurements at different frequencies. At all times the MRA was connected to the 130 ohm load resistor. At each frequency we made the following measurements with the MRA connected to the AC signal source. F source frequency, measured with a Fluke 87. Then MRA voltage across the source terminals with the MRA connected, Fluke 87. Vout DC voltage across the 130 ohm load resistor and current meter, Micronta. I out DC current through the 130 ohm load resistor, Micronta. Then digital recording of the input voltage trace covering about 4 cycles, Lecroy. In digital recording of the input current trace simultaneous with VEN, Lecroy. At each frequency we also disconnected the MRA and measured VOPN the open circuit voltage of the source, Fluke 87. We then connected a decade resistance box across the source terminals and by trial and error determined requive the resistance required to produce the same driving voltage as with the MRA connected. Results tilde. The following table shows these measured quantities for 4 different frequencies, beginning at resonance and then decreasing. Frequency in kHz 33.84 magnetic resonance amplifier input voltage 21.06 open circuit voltage 23.36 equivalent resistance 140 ohms output voltage 18.68 output current 0.1324 amperes. Frequency in kHz 33.56 magnetic resonance amplifier input voltage 23.84 open circuit voltage 24.04 equivalent resistance 1900 ohms output voltage 15.02 output current 0.1068 amperes. Frequency in kHz 33.34 magnetic resonance amplifier input voltage 24.20 open circuit voltage 24.10 equivalent resistance negative output voltage 9.75 output current 0.0696 amperes. Frequency in kHz 32.47 magnetic resonance amplifier input voltage 24.58 open circuit voltage 24.26 equivalent resistance negative output voltage 5.28 output current 0.0377 amperes. The first entry in the table is at resonance and is characterized by the highest Vout value. The second entry has Vout at approximately 85% of the maximum value as suggested by McLean and Wooten. The digital data for VEN and IN are not presented in this table in the interest of brevity. The several pages of digital data generated for each line in this table are, however, available upon request. The next table shows the results of the power calculations, both by the V2/requive method used by McLean and Wooten, and by the averaging of VEN times in using the digitized data. Also tabulated are efficiency figures for each method, i.e., output power divided by input power. Frequency in kHz 33.84 DC output 2.473 volts power dissipation 3.168 watts average input voltage 4.566 effective power 0.78 effective input voltage 0.54. Frequency in kHz 33.56 DC output 1.604 volts power dissipation 0.299 watts average input voltage 3.265 effective power 5.36 effective input voltage 0.49. Frequency in kHz 33.34 DC output 0.679 volts power dissipation negative average input voltage 1.467 effective power negative effective input voltage 0.46. Frequency in kHz 32.47 DC output 0.199 volts power dissipation negative average input voltage 0.401 effective power negative effective input voltage 0.50. The figures in columns 2 to 4 are in watts. The last two columns contain ratios. The column labeled MCWEFF is the power efficiency calculated by dividing the DC output by the McLean-Wooten input power V2/requive. Discussion. The second row in the table shows the condition that McLean and Wooten interpreted as over unity performance, for example, an efficiency of 5.36. The problem lies in the value of 1900 ohms for requive. This value was obtained because of the small voltage change between open and closed circuit conditions, 24.04 to 23.84, measured at that frequency. Note that at even lower frequencies, the source voltage was observed to actually increase above the open circuit voltage when the MRA was connected, a condition that McLean and Wooten also observed but did not attempt to analyze. At first glance this could be interpreted as evidence that the MRA was now feeding power to the source. However, this behavior is exactly what is predicted by classical AC circuit analysis when a load with a net capacitive reactance is driven by a source that has a net inductive reactance. Since the MRA is essentially a series LC circuit, at frequencies below resonance it will exhibit a net capacitive reactance. The audio amplifier used by McLean and Wooten has an output transformer which, at the MRA operating frequency, substantially higher than the middle of the audio range, will exhibit a noticeable inductive reactance in its output impedance. With such a combination of reactances one cannot, using only the magnitudes of voltage and current, determine the actual power being transferred to the MRA device. In particular, the Requivy method fails as one detunes from resonance because it ignores the effect of reactance. Such reactance creates a phase shift between voltage and current, a fact well known in the electric power industry as power factor. For example, if both voltage and current are sinusoids, true power is given by VI cos A, where A is the phase angle between the voltage and current waveforms. An equivalent method, which is more general because it is applicable to any waveform, is to average the product of the voltage and current waveforms over an integer number of cycles. This is the method we use to obtain the values in the second table in the column average Venn *in. Conclusion. Based on the results of our experimentation and analysis, we find that the MRA device provided by McLean and Wooten does not produce over unity efficiency results. The MRA circuit behaves instead as one would expect of a loaded transformer with a series capacitor in the primary circuit. When the MRA is detuned from resonance to frequencies slightly below resonance, the observed changes may give the impression that the MRA then draws unusually little power from the source while nonetheless maintaining a healthy output. This impression is false. True power measurements show that the MRA continues to draw about twice as much power from the source as it delivers to the load. Error analysis of MRA test results. Institute for Advanced Studies / Earth Tech International, Incorporated. Scott Little and H. E. Puthoff. February 1, 1995. Introduction. This analysis refers to MRA test results we presented in a separate report dated January 20, 1995, MRA TEST1ASC on KeelyNet. These results were based upon measured values of voltage, current, frequency and resistance. In this addendum, the magnitude of experiment error associated with these measurements is discussed and quantified. As will become evident below, the error analysis does not detract from our original conclusion, but rather strengthens it. Data. Frequency in kHz 33.84 magnetic resonance amplifier input voltage 21.06 open circuit voltage 23.36 equivalent resistance 140 output voltage 18.68 output current 0.1324 amperes. Frequency in kHz 33.56 magnetic resonance amplifier input voltage 23.84 open circuit voltage 24.04 equivalent resistance 1900 output voltage 15.02 output current 0.1068 amperes. Frequency in kHz 33.34 magnetic resonance amplifier input voltage 24.20 open circuit voltage 24.10 equivalent resistance is negative output voltage 9.75 output current 0.0696 amperes. Frequency in kHz 32.47 magnetic resonance amplifier input voltage 24.58 open circuit voltage 24.26 equivalent resistance is negative output voltage 5.28 output current 0.0377 amperes. Frequency in kHz 33.84 direct current output 2.473 equivalent resistance 3.168 average input voltage 4.566 effective input power 0.78 watts effective input voltage 0.54. Frequency in kHz 33.56 direct current output 1.604 equivalent resistance 0.299 average input voltage 3.265 effective input power 0.49 watts effective input voltage 0.49. Frequency in kHz 33.34 direct current output 0.679 equivalent resistance negative average input voltage 1.467 effective input power negative effective input voltage 0.46. Frequency in kHz 32.47 direct current output 0.199 equivalent resistance negative average input voltage 0.401 effective input power negative effective input voltage 0.50. Analysis. The data in the second line in these tables is of particular interest. That is the frequency at which the input power determination suggested by McLean and Wooten yields an efficiency of 536%, whereas our input power measurement yields an efficiency of only 49%. Let us examine the individual errors that contribute to the total error in our efficiency measurement, i.e., the 0.49 value that appears in the column labeled Venn** and EFF in the second table. This value is the ratio of the DC output power, 1.604 watts, to the AC input power, 3.265 watts in the column labeled average Venn**. The DC output power value was obtained by multiplying VOUT by IOUT. Both of these measurements were taken with Microntit 22-185A digital multimeters. The VOUT meter was connected across both the 130 ohm load resistor and the current meter so as to include the voltage drop across the current meter, so that the power dissipated in that meter would be included in the DC output power determination. It should be noted that a small amount of power, not included in our original determination, was dissipated in the VOUT meter itself. This meter has a 10 megohm input resistance and, at The 15 volts present in the second observation, was dissipating 22 microwatts. This should be added to the result of VOUT** IOUT to obtain the total output power. For the second observation, this omission results in a 0.001% underestimation of the output power, an error that will be seen to be insignificant when compared to the errors in VOUT and IOUT which directly affect the DC output result. The MFGR's literature on the 22-185A meter indicates that our VOUT measurement accuracy was ±0.8% relative and the IOUT measurement accuracy was ±1.5% relative. These errors are independent, so they add in quadrature to yield a ±1.7% uncertainty in the computed DC output, VOUT** IOUT. The errors in the average Venn** values are more difficult to characterize. The digital scope manufacturer's stated voltage measurement accuracy does not completely describe the errors that occur when two different waveforms are recorded by the scope and multiplied together. There is a finite amount of non-simultaneity, i.e., jitter, in the sampling of the two channels. When the two traces are multiplied together, the resulting error will be highly dependent on the actual waveforms being sampled. Therefore we elected to determine the error in the average Venn** value empirically. 10 sets of current and voltage waveforms were taken from the MRA device after it had been operating for about an hour to ensure thermal equilibrium. The operating conditions were similar to those in the second line of the data tables. The results of the Venn** averaging for the 10 sets were as follows: 3.26 volts, 3.24 volts, 3.25 volts, 3.20 volts, 3.20 volts, 3.29 volts, 3.16 volts, 3.24 volts, 3.18 volts, 3.27 volts. The observed standard deviation in these values is +/0042 watts. This is 1.3% of the mean value. Combining, in quadrature, this error with the 1.7% error in the DC output power, we get a 2.1% relative error expected in our Venn** and EFF values. That is, the 0.49 in line 2 should be interpreted as 0.49 ±0.01. Therefore, there is virtually zero chance that the conclusions presented in the original report were wrong due to experimental error. Our measured efficiency is 0.49 ±0.01. The McLean-Wooten value of 5.36 is 487 standard deviations away from our value. The probability of our reading being a chance observation, assuming that such readings exhibit a normal distribution, is astronomically small. Clarification of MRA test conditions. Institute for Advanced Studies / Earth Tech International, Incorporated. Scott Little and H. E. Puthoff. February 3, 1995. A number of persons have commented upon one particular aspect of the test conditions we employed to generate the data presented in our original report, namely the resistor we placed in series with our amplifier output. It should be noted that this resistor is controversial because the inventors of the MRA device have repeatedly claimed that, when they add such a resistor, the over-unity performance of the MRA is significantly diminished. As we emphasized in our original report, we conducted our tests with a Pioneer 160 watt power amplifier that had a much lower output impedance than the 35 watt Radio Shack amplifier used by McLean and Wooten. The resistor we added should be considered only as a modification of our power amplifier to make it match McLean and Wooten's amp. Some people have suggested that the presence of this resistor is the reason that our MRA device did not produce over-unity results. This is not the case. With the resistor present, we observed the same over-unity results claimed by McLean and Wooten when we used their measurement procedure. Specifically, at a frequency just below resonance, where the DC output is about 85% of maximum, we demonstrated with our equipment that the McLean and Wooten method of input power determination yields an efficiency of 536%. In other words, we reproduced the results of McLean and Wooten perfectly. The MRA worked just as they claimed it would. At the same operating frequency, we recorded high-resolution traces of input voltage and current with our digital scope and used them to compute the true input power to the MRA. This data showed the MRA to be only about 50% efficient. Therefore, it was not a matter of MRA performance but a matter of measurement technique that disconfirmed the over-unity results. In our original report, we explained why the methods of McLean and Wooten yield erroneous results. For the basic AC circuit theory that underlies our discussion, we would recommend any of a number of excellent texts on this subject, for example Principles of Linear Networks by Friedland, Wing and Ash, McGraw-Hill, 1961, MRA2, Magnetic Resonance Antenna. Further research by Norman Wooten, Joel McLean, Robert D. Taylor and Tim and Simplified Version. August 28, 1995. Tapping a new ambient power source by resonant excitation. It has been discovered that an apparently hitherto unknown or unexploited source of ambient power exists everywhere on Earth, extrapolating from experiments in Atlanta, GA and Austin, TX. And from which essentially free energy can be extracted at almost no cost, merely by using the key concept in the Wooten/McLean discovery, namely external harmonic excitation of a saturable core transformer, which causes it to act like an antenna that extracts ambient energy in amounts 19 times or more than the energy required for the harmonic excitation. Indeed, the original MRA design continues to work and to exceed all original expectations. In the MRA2 configuration, even when the piezoelectric capacitor has been removed and even when the primary resonance circuit has been cut, it still continues to produce verifiable output power. All that is required is a single wire from the AC signal generator to the saturable core transformer of the original MRA disclosure in order to cause useful power to be generated in the secondary circuit in amounts vastly greater than the power input from the harmonic signal generator. This appears to be an electrical analog of the chemical phenomenon of catalysis, namely the periodic pulses of energy into the transformer catalyze the transformer's nature so that it operates in an apparently hitherto never before seen mode, namely it behaves like a novel antenna which is extracting ambient energy from somewhere. It is not necessary to understand completely at this time what the source of ambient energy may be, in order to exploit the phenomenon in an environmentally benign way for the benefit of mankind. Numerous maverick scientists and engineers have suggested that there may be hitherto unknown aspects of electromagnetic radiation not comprehended in the standard Maxwell's equations, such as the controversial scalar waves postulated by retired Air Force Colonel Tom Bearden. Retired physicist Greg Hodownick, who duplicated the MRA independently after learning about it from the New Energy News newsletter, which reproduced the Internet announcement of Wooten and McLean, suggests that the ambient energy comes from the Earth's gravitational field and is somehow being converted into electrical energy. Former BYU professor of physics and astronomy, Dr. Bob Bass speculates that MRA2, as was the original MRA1, may be somehow tapping the ambient electromagnetic energy known to exist in the Earth ionosphere cavity in the form of Schumann resonances, which are continually resupplied every time a lightning bolt from a cloud strikes the Earth. As explained in the second edition of Jackson's classical book on electromagnetism, the great genius Nikola Tesla discovered the Schumann resonances experimentally 50 years before Schumann predicted them theoretically, says Bass, who adds that he once calculated that every cubic meter of space near the surface of the Earth contains on the order of 1 kilowatt of standing waves, similar to those in a microwave oven except at vastly reduced frequencies, which no one knows how to extract efficiently. Or do they? The late Utah inventor Murray, author of a book entitled The Sea of Energy in Which the Earth Floats, astounded famous scientists in the 1920s and 1930s with never-explained demonstrations of his ability to extract 3 kilowatts from nowhere at will, anywhere, even randomly selected points in the desert, using his unexplained Murray valve. Murray submitted a patent application, but withdrew it and his secret died with him. Admirers of Murray point out that his writings included the words germanium triode decades before the transistor was discovered by Bell Labs scientists, who won a Nobel Prize, and who had been directed into solid-state physics by the late Harvey Fletcher, who had earlier witnessed Murray's work and been shown every detail except the secret of the vest pocket-sized Murray valve. A recent controversial theory of Austin Institute for Advanced Study physicist Hal Puthoff and his collaborators Heiss and Ruda appears to explain gravity as not an intrinsic property of matter but as an indirect consequence of Maxwellian electromagnetic radiation, namely that, as earlier suggested by the late Russian dissenter Sakharov, gravity is a shadow effect similar to the accepted Casimir effect of quantum electrodynamics. Bass points out that if the Heiss-Puthoff-Ruda theory is correct, then Hadouinek's idea of tapping the Earth's gravity field in some electromagnetic way not hitherto suggested is conceivable. Whatever the ambient energy reservoir into which the MRA is tapping, the novel phenomenon is real and deserving of exhaustive further investigation, according to elated inventors Wooten, McLean, Taylor and McCracken, who urge independent investigators to seek to replicate their discovery. Part sources for the MRA Joel and Norm now report that stranded wire seems to be required in order to see the strange effects. The transducer used in the Keeling device was obtained from a surplus source local to Texas. We're trying to track down more of them. They apparently came from an industrial plastic welder. A lead zirconate titanate piezo transducer can be had from H&R Corp., but its dimensions are 2 dia x 0.1 thick, not the same as the original Keeling device. It has a 4.5 kHz resonance. Will it work? Dunno. They have several hundred in stock. H&R also carries numerous ceramic magnets, but it's unknown whether or not any are close enough to Norm's original that they will work. They offer one large ceramic magnet, 4x3x1, and have only about 50 in stock. This magnet has its poles on the flat magnet face, and has 2 poles on each face. At least 2 kinds of ceramic magnet exist, barium ferrite and strontium ferrite. It is not known whether both types work in this device. H&R Co., 18, Canal Street. This place has a great surplus mail order catalog.